Welcome back. So this is the continuation of the previous part. So in the previous part we have discussed two methods by an example, Jacobi method and Gauss Siedel method. So we wish to write now iterative process in a more general mathematical setting. So our goal is to derive the iterative methods for solving the system Ax equals to B. So for doing so, we are going to rewrite the above system as follows. So rewriting the above system in the following form, that is Qx is equals to Q minus Ax plus B. So you can see that Qx is added and subtracted, and the things have been arranged where Q is called the splitting matrix. So if we give them the numbers here, so this is number 1 and this is number 2. So equation 2, if you see carefully, equation 2 suggests the following scheme. Suggests the following scheme, that is Qx k plus 1 is equals to Q minus A xk plus B, which we will call equation number 3. So it is very clear that if so here k is starting from k is equals to 0, 1, 2, 3 and so on. So this will generate sequence of approximations given by x keys, right? So if I wish to write, so 3 generates x1, x2. So you are starting with initial vector x0, x1, x2, x3 and so on. For any arbitrary initial vector x0. So arbitrarily chosen initial vector x0. So there is no any restriction for choosing x0. But it is suggested that you choose good approximation for initial vector. Okay. So what is our objective here is this generated sequence should converge to the solution. If you look back and see if this sequence converges. So if you have this, if the sequence xk converges, then 3 automatically gives solution of 1, right? Because so it's very simple to see that limit of xk is equals to x. Okay, that this happens, this implies this, and equation 3 together implies x equals to qx is equals to q minus ax plus b in the limiting sense, and which if you rewrite it, this is ax equals to b, so hence the limit is the solution of the system. So if this sequence converges, so what will be the guarantee for the convergence of this generated sequence of approximate numbers? Okay, so from 2 and 3, what we have is, now we are making the following assumptions. The very first assumption is A is invertible, so that the system Ax equals to B has solution. Second assumption is Q is invertible. Q is invertible. Why it is so? Because you are going to solve this equation 3, right? So equation 3 is like Q of xk plus 1 is equals to y. Something. Okay, so this will have the solution only if Q is invertible. We are calling this, it is equation number 4. Now if we have the following assumptions, so 4 implies xk plus 1 minus x is equals to I minus q inverse of A times xk minus x. So if you repeatedly apply this recurrence relation, so this is equals to I minus q inverse of A to the power k plus 1 times x of 0 minus x. Now you use any subordinate matrix norm, then using subordinate matrix norm, what we get is norm of xk plus 1 minus x is equals to the norm of the right side, but if you use the subordinate matrix norm property, that is equal to less than equals to norm of I minus q inverse of A to the power k plus 1 norm times norm of x of 0 minus x. Now if you use the property called submultiplicative, so this will be further less than equals to norm of I minus q inverse of A to the power k plus 1 times norm of x of 0 minus x. So now from 5, so if norm of I minus q inverse A is less than 1, then 5 implies limit k norm of xk minus x is equals to 0. So this establishes the convergence. So what it has used, or what is the condition here is norm of I minus q inverse of A is less than 1. So if for a splitting matrix which you have chosen, the following condition is satisfied, that will establish the convergence of your iterative scheme. So this has been discussed. So again, it is not that, so for you have the splitting matrix called Q, which suggests the following scheme, and then where the initial vector x0 can be arbitrary. If you analytically, if you wish to write this xk is equals to I minus q inverse of A times x of k minus 1 plus q inverse of B. So theoretically this is right. However, we are not going to compute Q inverse here. We are going to use this as it is for the computational point of view. Okay, but on the other side, for the theoretical point of view, for establishing the convergence, we have worked with the following things. Okay, for the last equation, what we have seen in the right. Okay, so now let us write different type of methods with the given splitting matrix. Okay, so let's first method is Richardson method. Okay, so if you choose Q to be identity matrix, if the splitting matrix you have chosen is an identity matrix, then the process is given by this. So this process is known as Richardson method. Right? So for this case, what you require is, so for this, if you choose Q as to be identity matrix, so what is the sufficient condition? Is norm of I minus A strictly less than 1 with respect to any norm, any subordinate matrix norm. Okay, right. So with this you can, so you have to check with this infinity matrix norm, you can check. Okay, you can check with infinity matrix norm whether this is less than 1 or not. This is simple. Okay, right. So let's consider this example. Okay, so consider the linear system. Okay, so where you have the coefficient matrix, this is A and this is B. So I wish to check here the convergence of this Richardson method for the given A. Okay, so for the same I need to check the sufficient condition that norm of I minus A is less than 1 for some subordinate matrix norm. Okay, so so what is here is, so given A is equals to 1, 1 by 2, 1 by 3, 1 by 3, 1 by 2, 1, 1 by 2, 1 by 3, 1. So if you look at I minus, this implies I minus A is equals to 0, minus half, minus 1 by 3, minus 1 by 3, 0, minus 1 by 2, minus 1 by 2, minus 1 by 3, 0. And if you look at norm, infinity norm, that is going to be maximum of or row sum, okay, in magnitude sense. So 1 by 2 plus 1 by 3, 1 by 2 plus 1 by 3, 1 by 2 plus 1 by 3. So each row sum is 1 by 2 plus 1 by 3. Right? And this sum is nothing but 5 by 6, right? So that is equals to 5 by 6, and which is less than 1. So this gives you the convergence of the Richardson method. Okay, so you start with initial arbitrary, initial arbitrary vector, you start with 0, 0, 0. Okay, and then you get the good approximation x1, then you use x1 to get x2 for the Richardson method. So this gives you, so what is very important to know at first is the convergence, whether the this Richardson method converges or not. So this, the last line establishes the convergence of the Richardson method. Okay, right. So the next method which we have already learned is Jacobi method. So if you wish to write in the above scheme, if Q is chosen to be the diagonal matrix D in the iterative process whose diagonal entries are the same as in the matrix A, okay, then you have the process which is given by this. So let me explain here. So Jacobi's method we are talking about. So what we are taking here is Q equals to diagonal matrix. whose diagonal entries are the same as diagonal elements in A. Okay, so then what will happen? This will imply Q minus A is what? That is equals to D minus A. So the scheme is what? This is the scheme was Q of xk is equals to Q minus A xk plus xk minus 1 plus B. So now since Q is also assumed to be invertible, right? Q is also assumed to be invertible. So you have D inverse is very simple. So you can send it to on the right side. You write A is equals to L plus D plus U. So L is the lower triangular part, strictly lower, means the below diagonal entries. Okay, D is the diagonal entries and U is the strictly upper triangular. Okay, so what is the example? So example, if you wish to take, let's say A equals to 1 2 3 4. If I wish to write in above form, that is 0 0 3 0 plus 1 0 0 4 plus 0 2 0 0. So this is your L, this is your D, and this is your U. You write this in the following form. So this implies D equals to D minus A is equals to minus time L plus U. If you write it, okay, and the above scheme becomes dxk is equals to D minus A, that is minus L plus U, xk minus 1 plus B. Now you take the inverse both sides. So D inverse does not involve much computation, so you will no need to. So it's a direct, okay, minus D inverse of L plus U xk minus 1 plus D inverse B. So this is called Jacobi's method. For this, what you require? That you require norm of D inverse L plus U is infinity norm less than 1. If I wish to write on the matrix this D inverse of L plus U, that is equals to D inverse of D minus A, that is equals to I minus P inverse of A. Okay, now if you look at the generic element in matrix D inverse A are Aij by Aii. Okay, right? For with diagonal entries all are equals to 1, whose diagonal entries are equal to 1, right? Because D is the diagonal matrix whose entries are nothing but A11, A22, A33 and so on, A and N, right? Now this implies I minus Q inverse of A is the matrix whose diagonal entries are R0, and other entries are minus aij by aii for I not equals to 0. Right? So now this implies, if you look at the infinity norm of this and other entries in ith row and jth column. Okay, in the ith row and jth column. So if you look at the infinity norm of this matrix, that is nothing but maximum over 1 less than equals to I less than equals to n. This is maximum over row sum, right? So summation j is equals to 1 to n mod of aij by aii right. Now from here what we require, we require this is less than 1 for what type of matrices. So now if mod of aii is greater than equals to summation j is equals to 1 to n mod aij for all I, then norm of I minus q inverse of a, that infinity norm is less than 1. So this condition, so if for a matrix, if this condition is true, we say that the matrix is diagonally dominant matrix. Okay, so if matrix is diagonally dominant, then you will have the infinity matrix norm for which the sufficient condition is true. So hence Jacobi's method converges if you have the matrix which is diagonally dominant. So next method is Gauss-Siedel method, which you have already learned by an example. So if you wish to reframe that example in the more general mathematical setting, so if q is chosen to be the lower triangular part of A including the diagonal in the iterative process, so previously if you see, we have divided A into 3 parts, L plus D plus U, right? Then for this method q is chosen to be L plus D. Okay, so q has been chosen as L plus D for this matrix. Then the process will become here xk is equals to the following. So this implies q minus A is equals to minus U. Okay, so once you write here, so this process will become. So now if we wish to consider an example for Jacobi's method, we call the example where we have developed Jacobi's method and you can see Gauss-Siedel method. So if you look at here, so the matrix, the coefficient matrix A is diagonally dominant. So you can see the A11 is greater than equals to the sum of other row elements in magnitude. So 3 is greater than equals to 1. And second row A22 is greater than equals to A21. Okay, 2. So this is the, so note that this is the sufficient condition for the convergence of iterative method. So if you look at here in this system, in example, so you look, so here a11 is 10. 10 is certainly greater than 4 plus magnitude of minus 2, that is 6. The first row is diagonally dominant. For second row, you have magnitude of minus 10 is 10 is certainly greater than 1 plus magnitude of minus 1, that is 2. The third row, you have 10 is greater than 5 plus 2, that is equals to 7. So the considered coefficient matrix is diagonally dominant for the given. So this method definitely converges. Let us consider another method which is known as successive over relaxation method. So here Q is chosen as follows. So here Q is equals to W inverse of D plus WL. Okay, so W is also known as weighted. So if W is between 0 to 1, we will say this is under relaxation. If W is between 1 to 2, it is called over relaxation method. And when you say, see, if W tends to 1, so if you look at the matrix Q, if W tends to 1, so what you will, the Q matrix will tends to D plus L. And if you recall, where the Q is the D plus L is in the method called Gauss-Siedel method. Okay, so if W tends to 1, you will see then SOR method which you are going to consider for the particular problem, which actually tends to the Gauss-Siedel method. Okay, so this is another method which is given by the following splitting matrix. So what is D and L? So D and L are nothing but the diagonal entries. D is the diagonal matrix consisting the diagonal elements as A11, A22, A33 and so on ANN. And L is the strictly lower triangular part of the matrix A. Okay, so this is how we have learned three methods. Okay, so let's consider another system for an example. Okay, so here we have the following example. So here if you look at the coefficient matrix, okay, and if you look at the Jacobi's method, xk is equals to minus D inverse of L plus U times xk minus 1 plus B, if you recall. So now if you look at the norm of D inverse L plus U infinity norm, that is going to be 1.5. That is greater than 1. So for the particular system, so that you verify. Okay, so which tells you that Jacobi method need not converge. This will not say that this definitely will not converge. This will say there is a possibility that Jacobi method will not converge for the given problem. So what we will do, whether we should not go for Jacobi method or we should go for another method, Gauss-Siedel method or SOR. So definitely we have to look at it, okay, or we have to derive necessary and sufficient condition for the convergence of iterative methods. So this is an important result which we are going to use. The spectral radius function satisfies the following equation, in which infimum is taken over all subordinate matrix norm. So one way is we have already proved. Okay, so spectral radius of A is always less than equal to subordinate matrix norm that we have. For any subordinate matrix norm you consider, it will be always less than equal to CD. Okay, the other way is like, so this will imply spectral radius of A is less than equals to infimum over norm A, since infimum is the greatest lower bound. The reverse way requires some theory, so we are just keeping the proof of this result. Okay, right.